Okay, in this problem, we have a trapdoor that is being opened with a hydraulic cylinder extending at a constant rate of 0.7 meters per second. If the door is currently at a 20-degree angle as shown below, what is the current angular velocity and angular acceleration of the door? Observe that we can look at triangle ABC, and two sides of it, sides AB and AC, are given. The third side, which I label as L, has a changing length. Therefore, I can use this geometry, and using law of cosines, I can write the following. L squared equals to 1 squared plus 1.5 squared minus 2 times their product times cosine of the angle between the two sides. Let's label this angle theta in general. So this is a relationship that I can write for triangle ABC in terms of theta, length L, which is a linear displacement, in terms of angular displacement theta. Now, for the position shown where theta is 20 degrees, I can plug 20 degrees and solve this equation for length L at the position shown. Therefore, I have square root of, let's see, 3.25 minus 3 cosine of 20. Calculating this value, I get a length of 0.656 meters for the current position shown. Now, I have a position function. By definition, if I take time derivative of both sides, I can find a relationship between speeds, both linear and angular. So derivative of the left side with respect to time using the power rule is 2L L dot equals to, if I add those numbers, I have 3.25 minus 3 times cosine of theta. Derivative of cosine of u, recall, is minus u prime sine of u. So I have minus theta dot sine of theta. If I simplify this equation, I will get 2/3 of L dot equals to, I made a mistake here. Derivative of this value is actually 0. So what I have at this point is theta dot sine of theta. Note that this is a speed equation. L dot is linear speed of the hydraulic cylinder, which is given as 0.7, and note that it is constant, meaning L dot is constant, therefore L double dot is 0. So as far as angular speed of the trap door is concerned, I have this equation. I can plug numbers in it and find the angular speed theta dot. But before dealing with numerical values, observe that if I take time derivative of equation 1, I get an acceleration relationship. So let's do that before dealing with numerical values. Time derivative of both sides. Observe that on the left side I have a product, therefore I have derivative of first times second plus first times derivative of second, but L double dot is 0, so I can ignore this term. And as far as the right hand side is concerned, again I have a product, so I have derivative of first, which is theta double dot times second, plus first times derivative with respect to time of sine of theta, which is theta dot cosine of theta. If I simplify this equation and solve for theta double dot, I have a relationship for angular acceleration. So let's solve this for theta double dot. Theta double dot is going to be, and this fraction whose denominator is sine of theta, whose numerator is 2/3 of L dot squared minus theta dot squared times cosine of theta. So I label this as equation number 2. Now if I plug numerical values, the given numerical values, into equations 1 and 2, I will find the numerical values for angular speed theta dot and angular acceleration theta double dot. Solving equation 1 for theta dot, we get theta dot equal to 2/3 of L dot over sine of theta. Continuing with numerical values, we have 2 times length, which was 0.656, and then L dot is given as 0.7 meters per second divided by 3 sine of 20 degrees. Taking a calculator and doing the numerical calculation, we'll end up with 0.896, and the units are radians per second. And note that this is a positive value, meaning that the trapdoor is turning in counterclockwise direction. So this is what we get out of equation 1. If I solve equation 2 for theta double dot, I will obtain the following relationship: 2/3 of L dot squared minus theta dot squared cosine of theta, the whole thing divided by sine of theta. So this is what I will get for angular acceleration of the door. Continuing with numerical calculation, I will get theta double dot equal to, the current position is at 20-degree angle, so the denominator is sine of 20, and in numerator I have 2/3 of L dot squared, which is 0.7 squared, minus theta dot squared, or 0.896 squared, times cosine of 20. Taking a calculator and getting a numerical value for theta double dot, we end up with theta double dot equal to minus 1.25, and the units are radians per second squared. Observe that this negative numerical value indicates that the trapdoor is still turning counterclockwise, but its angular speed is slowing down, indicating that angular acceleration is negative or clockwise.